Thanks. Okay, so as you were warned, I'm a psychologist, and I'm interested in predictions. This is a research with my ex-student Eyal Art and current student Ori Plonsky, who is here, and the Cohen brother, Doron Hamzat. It's currently in Press in Psych Review, and the paper is also on the web if you will be interested. Okay. So what we do in that paper, we're going to present a critical review of basic research in behavioral economics, and we'll try to clarify the implication of this research to mechanism design. I think this is appropriate because many of the talk here, until the last two talks that I heard here, basically elegantly ignore behavioral economics and assume that people basically maximizers. And so I'll give you you can benefit twice from my research. First, because a critical element of the way I'm going to review the literature can help you justify why you ignore behavioral economics. But hopefully I can also convince you that there is a way to use behavioral economics. In addition, I hope that this paper can be used for teaching, because basically we're going to review all the classical phenomena in decision under risk and uncertainty in one experimental paradigm, so it's very easy to teach this stuff. And also, if you guys are not expert, I'm going to tell you about review this literature for you. And also for model development, because we collected a huge data set and organized a choice prediction competition. And all the data on the web can be found. The link is in the paper. The starting point of our research is the observation that research in behavioral economics is often criticized on the ground that it highlights interesting choice anomalies, but it rarely supports clear predictions. So we know that people deviate, people are not rational in many ways, but it's not easy to predict how they will deviate from the rational model. The main reason for the difficulty is that the classical anomalies are explained by several models. And in many cases, this model suggests different psychological tendencies. And it's not always clear which model should apply in each situation. My friend Al Ross clarifies this critique by saying he really likes psychologists, he even marries psychologists, but he has some difficulty with our research. So unlike economists who have the wrong model, you guys have the right model, but I rarely know which model to use. So he asked that we add a 1-800 toll-free phone number to our paper and be ready to answer call which model to use in a particular mechanism design problem. So we try to address that. Kahneman and Tversky and the classical research that led to Kahneman's Nobel Prize tried to address this problem by considering 4 different choice anomalies and present one model to capture all of them. In particular, they focus on the certainty effect, also known as the Allais paradox, that led to Allais' Nobel Prize. So there are already 2 Nobel Prizes in this short paragraph. The reflection effect, loss aversion, and overweighting of error event. By the way, if you don't know this phenomena, I'm going to review them in a minute, so don't worry about it. All the research Kahneman-Tversky study was similar to the last 2 talks, was decision from description, and one-shot decision from description. For example, they asked subject to select between 3,000 lirot, it was here in Israel in the 70s, with certainty, or 4,000 lira with probability 0.80 otherwise. Okay, so they run many experiments for one-shot decision and then find these 4 deviations for maximization and then present the model. The success of follow-up research led many other researchers to try to extend prospect theory to capture other phenomena. And there were many other phenomena that people try to consider. The 2 classical phenomena, the Ellsberg paradox and St. Petersburg paradox, that started all this research in decision-making. People try to explain them with prospect theory and then some other phenomena. So there are 14 different phenomena that when I teach decision-making, I teach in my class, and I will review most of them for you. But it's turned out that it's not easy to capture all of them with prospect theory. In particular, this research, the effort to capture all these phenomena with prospect theory suggests, or with different generalization of prospect theory, suggests that you did different addition, different assumption to add to this model to capture the different phenomena. So we didn't really solve the problem of having one model to predict choice behavior among gambles, which is what we're going to focus on. In particular, the most important problem that is turned out to be a very large difference between decisions that people make when they, in one-shot decision based on the description of the choice task. In this case, people behave as if they overweight rare event. But when people can rely on past experience, they behave as if they underweight rare event. Okay, so we get description experience gap. Overweighting of rare event in one situation, and once people start getting experience, they underweight rare event. Now, so you could say, okay, maybe we have a different model for one-shot decision without feedback and decision with feedback, but most real-life situations fall in between. In particular, if you want to design a mechanism design or some menu and let people decide, initially they make decision based on the description. They can still use the description, but they also have experience. So important question is how people behave when they can have both experience and description, how they combine the two sources of information. So because we don't know, so we still have the 1-800 critique by Alroth. Okay. So, and as I said, this is one justification way where many people in this conference basically ignore the behavioral research. Say if sometime you get overweighting, sometime you get underweighting of an event, maybe we can just assume expected value maximization. So we try to do better. And how are we going to do it? Let me try maybe to stand here so I don't have to look back. Okay, so basically what we try to do is to extend Kahneman-Tversky's research and try to capture all the phenomena I've shown you with one model. Unlike most previous research, we will not just try to generalize prospect theory, but we're going to use the method Kahneman-Tversky used. In particular, what we do, we focus, we try to replicate all the phenomena in one experimental paradigm and then find the models that capture all of them. And to make sure that we don't overfit the data, we organize a choice prediction competition. Some of you got invitation to participate in the competition, and some of you, like Gali, actually participated. Okay. So here is how we organize this competition. At the first stage of organizing this competition, we identified an 11-dimensional space that in theory can give rise to the 14 most important deviations from maximizations that we know of. Then we run experiment, study 1, in which we try to replicate this phenomena in our experimental paradigm. And the result that I'll show you in a minute shows that we can replicate most of these phenomena. And by reviewing on it, I'll remind you or teach you what are those phenomena if you're not enough behavioral economist. In study 2, we draw 60 randomly selected problems from the same space of choice task. And then use the data. And then we had already 90 problems. And then we use the data to try to find a model that will capture all the problem that we studied, the 90 problem. Then we publish the data on the web, all the 90 experiments and our best model. And we challenge other people to participate in experiment to predict the behavior of 60 other problems to be drawn from the same space of same 11-dimensional space of choice task. Okay, and that was a competition. So let me start by showing you the 11th dimension.
What was the incentive for participating in the competition?
Well, the incentive was to be a co-author of the paper, which turned to be not so bad. It's actually 2 weeks ago was accepted in Psychological Review. It was for psychologists. It's the best you can do. So the Cohen brothers, which are not really biological brothers, are the winner of the competition. Ori and Eyal and I organized the competition. Okay. So each problem in our space is a choice between two basic prospects. Option A that gives some high payoff with some probability and low payoff otherwise. And option B that gives some lottery with some high expected value with some probability and low payoff otherwise. The lottery itself is defined by two additional parameters, the number of possible outcomes. So option B could have, option A had up to 2 possible outcomes, option B had up to 11 possible outcomes, and the shape of the lottery. In particular, we manipulated the correlation between the outcome of the two lotteries. 10th parameter was ambiguity, whether there was some ambiguity. In most problems, there was no ambiguity. We told the subject the exact payoff distribution. In some problems, they didn't know the probability. And the 11th dimension was studied within problem, was the feedback. each subject first face each problem 5 times without getting any feedback, just based on a description. And starting from trial 6 until trial 25, because each problem was studied for 25 trials, they could get feedback after each choice. So they could base their decision, both of them, on the description and on their experience. Yes?
Correlations between A and B? Or between
Correlation between the realization. I will show example.
Of A and B?
Yeah. Okay. So here is how a typical choice task. In this task, the subject was asked in trial number 1. So each subject faced 30 decision problems, each one of them for 25 trials. In trial number 1, subject will ask, you can choose between A, that give you 3 shekel with certainty, or option B, that give you 4 with probability 0.8, 0 otherwise. The subject receives some show-up fee in shekels, and then they could either gain or lose money based on their choice. Each subject, as I said, faced 30 times 25, 750 problems, but we paid for only one randomly selected choice problem. So in this task, the subject may think, well, okay, look at this. This doesn't move. Okay, maybe the subject select, let's say that the subject come here and select B, and then he gets the following feedback. You selected B, and that's the only feedback he gets. In the first 6 tries, because the first 6 tries we didn't give them feedback about the outcome, we only remind them what they selected. And then they continue 5 trials, and then they get to trial number 6. And in trial number 6, if the subject selected, for example, B again, you got the following feedback. You selected B, your payoff in this trial is 4. Had you selected A in this case, you would get 3. Okay? So this is how a typical problem was studied. The problem with ambiguity was presented in the following way. You can choose between A that give you, in this example, 10 with probability 0.5, 0 otherwise, or B that give you either 10 or 0, but you don't know the probability. But you know that the probability are fixed. So this was a question about the experimental design. Okay. So here are the main results. And as I said, I will try to remind you of the classical phenomena in behavioral economics while presenting it. So I first want to remind you what is a Allais paradox. The Allais paradox is a comparison of these 2 problems, problem number 1 and problem number 2. In problem number 1, A gives 3 with certainty, and B gives 4 with probability 0.8, 0 otherwise. Problem number 2 was created by dividing the probability of high prices in problem number 1 by 4. According to expected utility theory, the division of all the pair of this transformation should not affect preference. So expected utility theory has no prediction what people would select in problem number 1, because it depends on your utility function. But if you select here A, you should also select A prime here. This is a prediction of expected utility theory. The common results when subjects make decision based on description is that most people like the safe prospect here. They select it 58% of the time in our replication. But after the division by 4, most people prefer B. They don't like A anymore. And this Kalman-Tversky explained this phenomena, called this phenomena as a certainty effect. They suggest in prospect theory that people like the safe prospect more when it provides sure payoff with certainty. Okay, so this is one phenomena. So what happens when we give people feedback? It's turned out that feedback eliminates this puzzle. So it is true that without feedback in the first block of 5 trials, we get deviation from expected utility theory in the direction of the certainty effect. But feedback very quickly eliminates that. Even 20 trials with feedback, we already get a little bit of a reversal here, but the difference is insignificant from here to here. Okay, so this is one phenomena, and our task is, what we want is to predict also the existence of the Allais paradox and the fact that experience eliminates it.
But Ido,
Yes?
even from the second trial, it looks like it doesn't really.
Yes. In fact, the Kalman-Tversky phenomena, as you'll see, they disappear. 3 trials with feedback already eliminates them. This is what happens here. Even in the second trial, it's insignificant. So the phenomena, this famous phenomena are replicable, but are not robust. Experience very quickly eliminate all of them, but one.
So it's experience, but not feedback only.
Oh.
The sixth one.
Oh, no. You see here block of 5. So this is the first block with feedback.
Okay, that explains
Yeah. No, it's definitely the feedback. I'll show you later data that shows it's the feedback and not the experience.
the block. Okay.
Yeah. Okay, thanks for the question. Another phenomenon that Kalman-Tversky found was a reflection effect. And this is a finding that people are more risk averse in the gain domain than they are in the loss domain. In this case, proportion of people select the risky prospect was 42 here. So most people avoid the risky prospect, but here people were basically indifferent between the risky and the safe prospect. And the question, what happened when people gain experience here? And the answer is that in this case, the phenomena is flipped. And in this case, the learning is relatively trivial. They learn toward maximization. In this problem, the top problem here, they learn to prefer the 4 with probability 0.8 that give expected value of 3.2 over the 3. And in this problem, they learn to avoid the gambles that give a negative expected value of minus 3.2 and prefer just a short loss of 3. So in this case, experience just moves people toward maximization. But as I'll show you in a minute, this is not a general result. There are situations in which experience moves you in different directions. Another important phenomena, yes?
That's expected value, not utility. It's not like other paradox where you know that if there was expected utility, you know that
Yeah.
one and problem got the same. Here, that's different numbers.
Yes.
You cannot deduce
Yeah.
anything.
When I talk about maximization, I talk about maximization of expected value.
Value.
Yeah.
Yes. It's important.
I'm going to only focus on maximization of expected value. I happen to think that Bernoulli was the first behavioral economist, and he already had too many free parameters. Okay, so I like expected value. Okay, here is another problem. In this problem, people have to choose between 2 for sure, or a gamble with expected value of 2 that give 101 with probability 1 in 100, 1 otherwise. As prospect theory predict, people behave as if they overweight rare events. They prefer the long shot gamble over the sure thing. In the loss domain, we get the opposite. People try to avoid the gamble minus 20 with probability 0.5, 0 otherwise, but the effect is not very large. So according to prospect theory, people should really, in the original papers, they get larger effect. They get 80% here and 20% here. We don't get these numbers, but they study hypothetical choice. We study choice among real gambles. And the effect is smaller, but is in the direction of prospect theory. What happened when people gain experience? Again, it's reverse. People initially have a small bias toward overweighting of a rare event, but when they gain experience, they start behaving as if they're underweighting a rare event and behave as if it won't happen to me. So proportion of people that want the 101 with probability 1 in 100 was 55% here, but it goes down to 42%. Notice that this learning effect happens despite the fact that experience does not add, feedback does not add any information, because the subject have full description of the gambles. Nevertheless, experience teaches them something. We're not sure exactly what. Sergio.
No, I was just thinking that somebody who got 101 at experiment 5 would think that I'm never going to get it again and will switch to 2 or certainty for a very different reason than what we're talking about.
Yes, that could be, but that's the challenge is to predict. So you could predict, you could participate in our competition, and in the next competition maybe you can participate.
When running this in the
Huh?
lab, when presenting these problems in the lab, you presented the top one as lottery and the bottom as insurance, or use the same names?
No, it's the same name, option A or B. Yeah, we don't call it. Yes.
Putting the learning effect aside for a second,
Yeah.
aren't these results somehow in contrast to empirical evidence showing that in general people are converging to EMB when you increase the number of iterations that you have?
Converging to what? To
EMB behavior.
to expected value maximization?
Yeah, expected monetary value.
No, I'll talk in a minute. In some situations, people learn to maximize. In other situations, they are not. And I will. One of the goals of the participant in the competition, this is my main goal, is to know under which condition people will learn to maximize. And I think that once we understand that, we can do better mechanism design that are robust. This is not always the case, and our main goal is to try to discover when people learn to maximize and when they do not. And when they do not, in which directions they are going. So let me show you some more data, and then we go back to the model. And next phenomena is loss aversion. Kalman-Tversky found that people tend to have loss loom larger than gain. People don't like gamble with mixed outcome. We get this phenomena initially, but again, experience eliminate it. In this case, they can get 13 for sure, or a gamble that lead to loss in 40% of the time, and lower expected value of 12 shekel only. But experience, for some reason, leads them to prefer this gamble. You see here learning in the opposite direction of maximization. See, this has a lower expected value of only 12. 20 tries go up from 35% to 50% selecting this gamble. So here is learning against maximization and against expected, against loss aversion. Okay. Next phenomena is simplified version of the St. Petersburg paradox. In this case, you can choose between 9 for sure or a gamble that pay either 2, 4, 8, 16, 32, 64, 128, or 256. And here, there's not much learning. They don't like this gamble. Proportion selecting it is 38, and it goes down to 36. Experience does not change the tendency to behave as if you are risk-averse in this version of the St. Petersburg paradox problem. Yeah.
Those of us not familiar with this, could you say why it's called a paradox?
Well, it's called paradox. There's no paradox here. The original problem, you were told, you come to a casino and there is a coin, you can flip it until the first fall on head. And then your payoff will be 2 to the power of k. K is the number of flips. So if you compute the expected value of this lottery, it's infinite, but most people are not willing to pay more than 8. Okay, thanks for the reminder to explain it. But of course, in our version, we didn't do that because we pay real money and we didn't want to lose infinite. Okay, so.
What is the expected value of option?
Well, there was 9 in both cases. Yeah.
It's 9.
It's exactly 9. Yeah. Okay, so the behaviors are risk averse in this problem, and experience doesn't change that observation. Another famous phenomena. Yeah. Okay. The next one. Look at this is known as a Ellsberg paradox. In this, look at the black problem. It's 10 with probability 0.50 otherwise, or 10 or 0 with unknown probability. Initially, people exhibit ambiguity aversions. They don't like this gamble, and they select it only 35% of the time, 37% of the time. But with the experience, they quickly go and become indifferent. And
how did you generate the experience?
Well, in this case, the experience actually reduced ambiguity, but it did not eliminate it.
No.
Oh.
How did you get?
Oh, it was 0.5.
With what probability?
It was 0.5.
Oh, you used 0.5.
We used 0.5.
So they figured it quite quickly.
Yeah, they figured it very quickly, yeah. But so you get some ambiguity aversion, but after a few trials with experience, the fact that you know less doesn't make it less attractive. The last experimental phenomena here that we call regret is another one of these problems that we get learning in the opposite direction. Look, the black problem is pretty trivial. Here you get, and this is how we manipulated correlation. Here you get 6 if event E happened, 0 otherwise. And option B, you get 8 if E happens, 0 otherwise. So our subject from Technion and Hebrew University are not stupid. They tend to prefer the 8 over the 6. Initially with 97% go up to 99%. In this problem, an event E occurs with probability 0.5. In this problem, the same event E, but now you get 6 if E happens, 0 otherwise, and here you get 9 if E doesn't happen. So of course, this is a much better lottery, but here experience, so initially they select it 96% of the time, but experience reduce the choice rate of this option, of this attractive option, from 96% to 85%.
No, so you say 5 is the end of
Huh?
block 5? Sorry.
What?
5 means end of block 5? What does 5
Yeah, end of block 5, yeah.
So it's after seeing 4 blocks with data.
Yeah,
With real data?
yeah.
So the head statistics of each block is 5 or the head statistics of
Yeah, of about, the last trial was based on 18 tries in which you got feedback.
Nevertheless,
Yeah, so they learn in the opposite direction. And maybe this is related to what you said, Sergio, that they say, oh, I was already lucky. Now it's basically what we think happened. And
some of them got the wrong draw. So
Yeah.
some of it can be explained because their experience is that they got good outcomes or bad outcomes.
Yes.
And that came by chance. And that makes
yes,
sense.
but we tell, basically what happened, we tell them the pair of distribution, we don't lie, but they behave as if they don't trust us. But sometimes in the opposite direction. Sometimes we don't have only positive recency. Some of them, as you said, after I got 101, I'm not going to get it again. And some they do. They basically behave as if they try to discover patterns. This is our story, what we think they are doing here. Okay, then study 2, we collect some more data. One interesting finding that we get there is that when you have 13 for sure or gamble with symmetric distribution with mean of 13, people are indifferent. We don't get risk aversion in this kind of problems. But basically we got the same kind of phenomena. And then we also, this is related to Michal's question, when do they change their behavior? Is that the feedback or the experience? So you see here, this is the data I've shown you, the blue line. And you see here by trials, the 25 trials. These are all the problems in which there was a rare event, and we looked at the proportion of time in which they behave as if they overweight a rare event. So initially, without feedback, repetition increased the tendency to overweight a rare event. That is to behave according to prospect theory. Once they start getting feedback here, then it goes down and the underweight a rare event. In this experiment, they got feedback from the very first trial, so they go down immediately. So basically, the feedback leads them to behave as if it won't happen to me. But if they make the same decision again and again without feedback, then they actually tend to overweight a rare event. Okay, so now we thought, how can we explain those funny phenomena? Here is a summary. First, we could replicate the classical decision phenomena, choice anomaly that we teach in decision-making courses. But with the exception of risk aversion in the St. Petersburg paradox, these phenomena are not robust to feedback. Feedback eliminate or reverse many of them. Our effort to try to find a model that captures everything suggests, so initially we tried to find some version of prospect theory or expected utility theory or some other popular model in the literature, and we couldn't capture the results with this model. It was very difficult. If you want to do it with prospect theory, you have to assume different parameters in different problems. So that was not successful. So what we did notice, that you can explain at least verbally all the results with the idea that people come to the lab with 4 different tendencies. First, they are pessimists. They think the worst outcome going to happen. Second, sometimes they think, well, everything can happen. 101 with probability 1 in 100 or 1, who knows? They are both equally likely. This is a different bias they could exhibit. Notice that it's inconsistent with this bias. This one say, pay attention to the worst possible outcome. This one say, everything is equally likely. A third bias that they could think of, that we think the data suggests, is that they say, well, the most important thing is to earn money here. I shouldn't worry about the number. Let's get the perf sign correct. And then another effort that they could consider is try to minimize the probability of regret. Not average regret, but the probability of immediate regret. I want after this trial to be happy with what I did. This effort can lead to underweighting of rare event because, for example, in the 101 in probability 1 in 100, in 99% of the time, if you select the gamble, you regret later because you got only 1 and you could have gotten 2. So this leads to underweighting of rare events. This leads to overweighting of rare events. This leads to risk aversion. And basic research in psychology typically don't present this explanation because we don't like hypotheses that lead to contradicting prediction. We thought that maybe all these things work together, and also we thought that maybe feedback, the main effect of feedback is just reduce the first 3 biases and increase the last one, lead people to behave as a minimize the probability of regret. And this is the reason why feedback leads people to behave as if they underweight a rare event. And then we try to quantify this model, and we come up with a model that we called BEAST, for best estimate and sampling tool. And this is the best model that we could find. As I said already, it was very different than prospect theory and the other popular model in the literature. It also doesn't assume cognitive limitation like most psychologists like to assume, because it's basically assumed that subjects first actually behave as if they compute the expected value, and then on the top of that, they are not sure that they trust this computation of expected value, and they behave as if they take more samples from the payoff distribution. But the samples, 3 of them are biased. So they take one sample that is basically pessimistic, another one uniform, another one more sensitivity to the payoff sign. And then they also take unbiased sample. It's turned out that if you take unbiased sample from the payoff distribution, but you take small sample, that will lead you to behave as if you try to minimize the probability of regret. This is a point. And basically what our model suggests that with experience, feedback basically increases the tendency to take unbiased sample. And this is why it's increased the tendency to behave as if you underweight a rare event and as if you try to minimize the probability of regret. So this is the best model that we could find. And the model could fit all the 60 data set, the 90 data set from the first 2 experiments. And then we publish it on the web and challenge people to come up with better model. So specifically, we said we presented BEAST. It's a little bit ugly model. We hope that you guys can come up with beauty. Present a better model. So we did that in December 2014, and basically said that we're going to run study 3 few months later, and the submission deadline was 6 months later, and we accept submission in R, MATLAB, or SAS. 53 teams registered to participate, but not everybody end up participate. Maybe because we're not sure why, but it was not so easy to participate. You have to. It's not easy to capture all this phenomena with one model, but some people were successful. So 25 we got 25 submissions from 5 continents. So we're very proud of that. We had even one from Tunisia. But some of them, of course, were from the Technion, and from Hebrew. We also have a nice group from the Hebrew University. When you look at the submission, we had 4 groups who tried to use prospect theory-like models, but these guys did not do very well. We have 15 other teams that basically use some variant of BEAST. So they took our model, see where it's error on the first 90 problem, where it has large bias, and try to correct for it. And then we had 6 other teams that use theory-free, I'm not sure it's theory-free, but machine learning-based model. And the main result was that the top 12 models were some variant of BEAST. And the difference between these models was statistically insignificant. And the best machine learning model was submitted by Gali here. And it was also almost as good as BEAST. And if I understand correctly, you also use some BEAST-like features and use as a machine. Which machine learning algorithm? SVM. So this was almost as good, but did not beat BEAST. Here is how the results look. So you see here the prediction of BEAST and the experimental result, and there were some gambles in which BEAST was a little bit off. So the Cohen brother who won the competition, they basically correct these mistakes by adding some assumption to BEAST, and it's turned out to be successful. In additional analysis that I ran with Ori and Tamir Chazan and Moshe Tenenholz here, we try to understand why the machine learning algorithm were not more successful. So,
can you explain a little more what BEAST is? I'm sorry, I didn't really understand what.
Okay. Okay, thanks.
BEAST does.
Yeah.
I don't know if you want to do it now.
No, I can do it. No, basically what BEAST does, it first computes the best estimate of the expected value. So when there is full information, it just starts with the expected value. and then it's behave as if it's take small samples from the pair of distribution, the pair of distribution, and add them to the expected value. So you take, I think the best parameter was taking, huh?
From the feedback you give.
No, initially it's take from the objective distribution, but once it starts getting feedback, it starts taking it from its past experience. So in the first trial, it already takes samples, but then it takes samples from the objective distributions. But in trial number 7, it takes sample from its past experience. Or after trial 6, when it has experience, the samples are taken from the objective, from the outcome. But the samples initially are biased in this direction. You're more likely to sample the worst outcome if you use this sampling tool, or uniform if you use that sampling tool, or focus on the sign, or unbiased. If you sample unbiased, you sample from the objective pair of distribution. And if you are...
Sorry, I don't know. What do you mean all?
Huh?
It's a model. What
Yeah.
do you mean all? I mean, those things are not compatible. So what
Oh, okay. No. So the model specified that initially you have some probability of sampling unbiased. And this is a free parameter of the model.
So you put four probabilities on those 4 things, and you tweak them so that to fit
Yeah.
data.
Yeah, but we assume...
Find some number
Exactly. But we fit the parameters on the first 90 problems, and then use the same parameter to predict the next 60. And the main assumption here is that initially you have some probabilities, but when you start getting experience, the probability of selecting the unbiased tool increases. And that explains the experience description gap. So you don't have to assume different decision processes. You just have to assume a qualitative difference processes. You just have to assume a little bit higher probability of taking unbiased sample from the pair of distribution. Now you could ask, but why would you assume that subject behaves if they take samples? And Ori and Kinneret and I have a paper suggesting that people behave as if they take samples because they think that they detect some pattern, maybe similar to what you said. So they say, well, I'm now in trial 17. That's remind me of trial 12. So I'll do best reply to what happened in trial 12. This is basically the idea, that subjects are looking for patterns, and that leads them to behave as if they rely on small samples. Because if you think that trial 12 is more similar to trial 17, you behave as if you rely on your one past experience. Okay, so we go back to the question why it was difficult to beat BEAST with machine learning algorithm. And I initially hoped that there's something magical about psychology and new machine learning can never beat us in this data set. But unfortunately, Ori convinced me that the fact that Gali was really close and beating us was not a chance result. And if you use a little bit, if you change a little bit the features, at least, of course, this is thing we did in retrospect, you can come up with a machine learning algorithm that will beat BEAST. And the best version that we could find, as it again was in retrospect, was a version of BEAST that one of the features was a random forest model that one of its feature it's BEAST itself, and the other feature are other features that assumed by BEAST. And that one, for some reason, beat BEAST. I still not believe this result, and I want to run another competition and challenge other machine learning people to participate and see if we psychologists still have can earn money, and we should not all learn machine learning. But I'm just to minimize my risk, I'm trying to learn machine learning now. There's something powerful in this method, I begin to think. Yes?
The groups that participated in your competition, what disciplines they came from?
Well, we had the 6 machine learning algorithm was computer scientists. But other were psychologists. There are a few economists. You know how Dov Munders say how economists count. They count one, too many. They're not interested in numbers, the typical economist. So we had mostly psychologists and machine learning. And yeah. So my interest in machine learning is serious in the sense that I think there is something interesting in machine learning. So basically, the real deep question is, suppose that machine learning algorithm provides the best prediction. What does it tell us about the cognitive process? And I guess it tells us something. It tells us that maybe what people are doing, they also do, maybe. But of course, psychologists used to think that in the 50s, this was a Skinnerian psychology. It was a basic idea of Skinnerian psychology that people do what works in similar situations in the past. So psychologists of the 50s was basically machine learning, that the brain is basically a machine learning algorithm, that it try to find some similarity function and do what works in the most similar situation in the past. One of the problems of this Skinnerian psychology that psychologists in the 50s and the 60s try to find the one similarity function that best fits the data. And I guess that one thing we learned from the success of machine learning that you can do much better if you assume that many similarity functions are used in parallel. And I think that this is about time that psychologists will go back to their old idea by building on machine learning. By the way, you guys, computer scientists, confuse us. You know that the cognitive revolution in psychology happened in the 60s after Herb Simon understood how the computer works, more or less. And much of the research in cognitive psychology and all the cognitive limitation models based on the analogy of computer science from the 50s. So Ori and I and Moshe here think that maybe psychology can benefit from updating the analogy for computer science of the 21st century. And maybe we can improve our understanding of cognitive processes. But let me go back now to mechanism design. So here is what I think are the implications to mechanism design. And I said you guys can benefit from that in two ways. First, if someone tells you why you don't use behavioral economics, you say, well, IDOS expected value is pretty good, but there's a deeper way, of course. Basically, what we think we learn is that the decision from description phenomena, that is the Kahneman-Tversky phenomena. By the way, the last two talks that we just heard also focus on decision from description. And in decision from description, you do get deviation from maximization. They do show some sensitivity to expected value, but also some biases like pessimism, equal weighting, maximizing perf sign, and also minimizing probability of regret. These biases are in contradicting direction in some problem, but not always. So when all of them go in the same direction, we will get maximization, if all of them go in the direction of maximization. And if all four biases go against maximization, we'll see less maximization. So we learned something for what happened when people make decisions from description. But more interesting, I think, from mechanism design is the fact that we should not overgeneralize from studies that examine how people respond to description. Because when people start gaining experience, they start to behave as if they learn, and in particular, they learn to maximize when the options that maximize expected value also minimize the probability of regret. So I think that if what we want to do is do mechanism design that is robust, it's good to have these two criteria. The regular criteria in economics that make sure that what is good for society also good for the individual, that is maximize the individual expected value. But this is not enough. If you want people not to get confused, make sure that the optimal option for the individual also minimize its probability of regret. And if you do mechanism like that, there is good chance, I think, that it will be successful. Okay, let me give you an example. 2 months ago, there was an article in the New York Times talking about the apparent inconsistency between the success of Uber and the research by Kammerer, one of the most best-known papers in behavioral economics that were published in the 90s, suggesting that New York taxi driver work less when they earn more per hour. And they had some data to support this hypothesis, and they also have a theory. And they basically use prospect theory to explain it. They say, well, in days in which there is a lot of traffic, so the driver earns a lot of money per hour, they earn more money, but initially they have to pay $100 to rent the cab. And once they make this $100, they are more likely to go home. They feel they have no loss and they can go home. So when they make this first $100 fast, they go home. So that's an interesting explanation for funny phenomena, violation of mainstream economic theory. But Uber people did not know about this research, and they assume that the exact opposite is true, right? In order to make sure to increase efficiency, they pay driver more when they want them to work more, and it is successful. So the question is why Uber driver learn in these settings. My hypothesis is that Uber create an environment in which both passengers and drivers learn to maximize expected value, and also help the owner of Uber to make $71 billion. And how they do it? They have an algorithm that their application, if you are an Uber driver and you go home, you can still see how much you could earn ahead you work. So when there is a lot of demand for taxi driver, you could say, oh, I could make $62 now for 2 blocks in New York City. That was silly to go home. And when you work and the salary is low, then you go home. Yes?
Is it true for the same drivers? Because we could expect that perhaps other drivers who work part-time with Uber will see that they
Okay.
can earn more money income.
Yeah, so so there is a research by Uber statistician, and he argued that almost all the drivers behave in that way.
For the same driver.
Yeah, so the driver learned with Uber incentive structure is clear enough so people learn to maximize. So I think this is only one example. What we want to do when we do mechanism design, if we want to create a better world, and I think Uber is one of the best examples because they actually do something about pollution. If we create an environment that is easy to people to learn, this mechanism design is going to be robust. I also think that the matching algorithms that Al Roth and others promoted have the same property. If you do the right thing, you rarely regret for doing it. So, and another example, of course, is a comparison of first price and second price auction. Second price auction have this, at least when there's no uncertainty about the value of the good for you. In a second price auction, if you use a dominant strategy, you don't regret it. But if we do a first price auction and you play the equilibrium bid, most of the time you will be sorry. You say, oh, I did the equilibrium bid, that's very nice, but I should do an epsilon above the second bidder. So this is another example. So it's 2 mechanisms that may be the same from economic point of view, but if you believe that subjects learn from experience and they try to minimize probability of regret, second price auction will be more effective, maybe not for revenue, maybe also for revenue in that case, I have to think about it, than first price auction. So basically my suggestion is that I actually like the approach to focus on expected value. I think that economists forgot the expected value idea too quickly, and they moved to talk about expected utility, and that really makes them hard to predict anything because they rarely know what the expected utilities are. So expected value is good, but I suggest to stay with expected value, but then to do sensitivity analysis. If you come up with a mechanism that should work well under expected value, check if it also minimizes the probability of regret. And if you have several mechanisms that all of them do well expected value-wise, select the ones that also minimize the probability of regret. This is basically our suggestion for mechanism design. And this is basically my story. Thank you.